We're going to, it's time to start. At this point, we are going to transition, and we are done with trigonometry topics. Nothing that could be considered a trigonometry topic or going to happen. Actually, last chapter test was no trigonometry either, but we're going to start rehashing and extending some of the ideas you guys would have seen in Algebra 2. So we're going to go back and look at some of these function types. So talking about polynomials, rational functions, exponential logarithmic functions, add a couple like logistics in. We'll talk about sequences and series, but these would all be considered like pre-calculus topics, or like extending on these major function groups from Algebra 2. Yes.
Oh, there wasn't a review for the last chapter, right?
Correct. Yeah, because it was so light. We did it like in one day. And
Okay.
All right. So this chapter, we're going to talk about polynomials. Okay? So the first part we want to talk about are just like graphs. And what we want to talk about mostly here is some vocab, and how to locate certain kinds of points on the graph of a polynomial. So let's say that here's a graph of the polynomial. I'm just going to refer to this polynomial as y equals f of x. Okay? So there are three types of features we want to be able to talk about here. The first one would be the zeros for the function, i.e. the x-intercepts. So that's just the place where the graph is going to be crossing the x-axis. Notice that for a polynomial you can have multiple of these, right? The next type of point is called the extrema. There's actually 4 different types of extrema we could talk about. So those 4 types of extrema that we would talk about are absolute or global. You could use those 2 terms interchangeably. Maximums, actually the plural for maximum is maxima. Absolute or global minima, local maxima, and local minima. Now, any polynomial graph may have 1, 2, 3, 4, 0 of these. Okay? They may have all 4, they may have none of them. Is everybody okay? Do you guys remember what the difference is between a local maximum and a global maximum? So a global maximum or a point is a global maximum if its y-coordinate is bigger than or equal to all other y-coordinates in the graph. So, for example, this graph has no absolute maximum because we know that there is no biggest y-coordinate because this end of the graph has an arrow pointing up. It'll go up forever. So there is no single biggest y-coordinate associated to one point. How about an absolute minimum? Is there one of those?
No.
No, why not? Because the arrow's pointing down, so there's no lowest point. It goes down forever. So this graph has no absolute minimum or maximum. Everybody's okay? A local maximum means that in some open interval, I can find a highest point in that open interval. So basically, this guy would be a local maximum, because in its little neighborhood, it's king of the hill, so to speak. Is there going to be a local minimum? Yeah. It's right down here at this valley, right? Is everybody okay with how to identify a local maximum or minimum just by looking at the picture? Should be pretty easy, right? The last feature we want to talk about is the end behavior. So the end behavior is going to describe what the arrows on the graph are doing. Now in this polynomial, how many arrows do we have on this graph? 2. So we're going to have 2 end behaviors. Everybody's okay? To describe the end behaviors, I'm going to require you to do that using a limit notation. Okay? I'm going to help you decode symbolically what this symbol is that we're writing, so you understand like how to change it for the given problem. So this is the left end, and it points down. Everybody agree with that? This one would be the right end of the graph, and this one points up. Is everybody okay?
Why do you write out right? Why do you don't write out?
I'm just describing what I'm seeing, and I'm going to map that to the limit notation here. So I just wanted to like verbally say what it is that I'm looking at and show how that matches symbolically to what I'm going to write this time. Is that okay? Okay. I don't know if I answered your question or not.
So it's
Okay. Because I kind of cut you off because this is like a transitionary step that I'm just trying to illustrate. So, to write this, it's going to be limit x approaches f of x equals. Every single time, that much of the limit you will write. You just have 2 spaces to fill in. Okay?
wait, is the limit separated from operations?
You should think about it like as an operation. So there's like an implied like set of parentheses going on there. So anytime you write an end behavior, that much you're going to write. You just have 2 things to fill in, depending on what we see. Everybody's okay? So the piece associated with the x is going to represent the end of the graph that we're talking about, whether it's the left end or right end. And the box after the equal sign is going to represent the direction of the point, up or down. Does everybody feel okay there? So if I look at this end behavior here, it's the left end. So left is going to be negative infinity. And down is going to be negative infinity. So that's how I would write the end behavior for that piece.
What's that on top of like the x and negative infinity? Is that like
L-I-M.
is that for limit?
Yes. And I write my L cursive, or else it looks like a 1. And I just kind of drag the, a lot of times the end of my L becomes the line for my little lowercase I, and I just put a dot there.
Yeah.
Is everybody okay with what I've done here? So if I look at this other end, so because it's the right end, right is going to be positive infinity, and up is going to be positive infinity. Are we okay with the vocab and the notation that we presented to you here? These would all be valid test questions. If I give you a graph on a test and I ask you to draw in, the zeros and the asymptotes and the extrema, and write the end behavior using a limit notation. That's all something you should be able to do from looking at a picture. Everybody's okay? There's no calculation going on here. It's just like vocab is basically what we're talking about, right? So let's say we have this polynomial function. And I want you to write for me the zeros, the extrema, and the end behaviors. We'll reuse our calculator to do most of this work, okay? So if you have your graphing calculator with you, and you'd like to follow along, I invite you to take that out and do so. If you want to borrow one, I have 3 sitting on my desk right now. Again, you're welcome to borrow one to follow along with. If you don't have your calculator with you and you get home and you're like, ooh, how did we do this again? What should you do?
What do you check?
Cue up the video, right? And just follow along at home when you do have your calculator. Okay.
You just have to put it into the y.
So the first thing I want to do is to type my function into the y equals, because I want to be able to look at the graph of this. So I'll press the y equals button, and then just type in my function exactly as it looks like on my sheet of paper. Before I go to my next step where I'm going to ask to graph this thing, I want to take a look at the top here where it says plot 1, 2, and 3 and make sure none of those are highlighted. If any of them are highlighted, just move your cursor onto it, press enter to unhighlight it. Because I know we were building scatter plots in the last chapter, and probably some of us still have plots turned on from that. So we're going to graph this now. So typically, when I graph something, I'm going to pick zoom standard, just so I have a reasonable starting window. Zoom standard just sets the graph going from -10 to +10 on the x, and -10 to +10 on the y. If I can't see what I'm looking at, then I'll adjust those mins and maxes so I get a better picture of what's going on. But here looks pretty good, like I can see exactly what's happening. Everybody agree? So far so good? Okay. The first thing I'm going to do is I'm going to find my zeros. I'm not going to do this by hand. I'm going to have the calculator do it for me. The command that I need is I'm going to press the second button and then the trace button up at the very top row to open up the calculate menu. Which command sounds like the one I want?
0.
Wait,
0.
what did you press get there?
Second and trace up at the very top. So I'm going to pick the 0 command. Now look at the bottom of your screen. Your calculator says left bound. It's going to ask us 3 questions that we need to answer. So the left bound says, I need to know in between what values of x I need to look for this 0. So let's look for this 0 first, this one right here. So I need to move my cursor so it's somewhere to the left of it, down there. So I'm just going to use my left and right arrows to move my cursor so it's somewhere to the left of that 0 that we're going to look for. So that's good, right? It's to the left somewhere. And then I'm going to press enter once. Now it's asking me a new question. Look at the bottom. It says right bound. Now I need to move my cursor to the right of that 0, but not past another one, right? So anywhere in between those two zeros is good. I've passed the 0. I can tell because my y-coordinate is positive. Anywhere in between this 0 and the next one will be fine. I'm just going to press enter here. And then it asks for a guess. It doesn't matter. So just press enter where you're at. So there's my first 0. Tells me -3, 0. What did your error say?
Error bound.
Okay, so you must have had them reversed. Maybe you gave the right bound first and the left bound second.
How'd you get -3?
So you would have been, your right bound would have been too far. It was past the second 0, so it found the wrong one.
It wasn't. Where's the second 0?
Huh?
Where's the second 0?
So I see one here, and one here. It's just where it's crossing the x-axis.
So it's between the first two, it not past the last one?
I don't know what one are you talking about? What do you
The
mean by
last
one?
0 that's on the x-axis.
There are 3.
Yeah.
So I can't pick my left or right bound so that I'm including more than one 0.
Okay.
Or else the calculator doesn't know which one you want it to find. It's not going to find both of them. It can only find one of them.
Okay.
So if you're picking your left and right bound, you have to have only one 0 in between that range.
Okay.
Or else it doesn't know what to find. Yes,
So-
sir.
How did you get it where it says 0?
Huh?
Can you like it says the
Yeah, you haven't picked a guess yet. So just press enter.
Oh.
There. Okay. Find the next 0. Try this on your own. You're repeating the same process. We're just looking for another one of the zeros. There's 3 of them, so I'm going to have to do this 3 times. Is everybody okay? Once you've found the second zero, guess what I'm going to ask you to do? Find the third one. And your guess has to be in between the left and the right, too. That could give an error also. If you pick a guess that's outside of the bounds, maybe that's what happened, Hannah.
Okay. I just got -3 again.
Okay. Then you didn't have it. Then your left and right bounds weren't, like you would have needed one like there and one like there to find the -2.
Okay.
They have to be, the one you're looking for has to be the only one in between the bounds.
Okay.
Does that make sense?
Kind of.
Okay. So think about it as like you're telling the calculator where to look. And it's only the best way to do that is to have only one thing for it to find where it's looking. If there's more than one thing it could find, you don't know which one you're going to get. Right? So what you want to do is like narrow that search field for your calculator so that there's only one answer in between, and then you're guaranteed to get what you're looking for.
So can you find the absolute or the extremas with the calculator?
If there was one, this one there's not.
Yeah, okay.
It's,
Does the calculator look for the locals?
we'll show you how to do that in a second. Okay. Next, we're going to find the extrema. If I look at this, what type of extrema do I have?
Locals?
I have one local maximum
Local minimum.
and one local minimum. Now I'm going to find the coordinates for these, and we'll round those to like 2 decimal places or something, because they're probably going to be kooky decimals. Everybody ready? Okay. We are going to once again press second and trace. Which command do you think I need if I'm looking for the local maximum?
Minimum and max.
If I'm looking for the local maximum, I want maximum. Okay? It's going to ask me the same 3 questions. It's going to ask for left bound, right bound, and guess. So if this is my local maximum right here, my left bound I want somewhere to the left of it. My right bound somewhere to the right of it. I only want one extrema in between. So I'm just going to move my cursor so that the only maximum in between there is just the one. And then I'll hit guess, and there's my answer. We'll round that to 2 decimal places. How's this going so far?
Good.
It's good? Find the minimum now. It's the same command structure, except instead of using the maximum command, we're using minimum, but everything works the same way.
Wait, after you find the right bound, you press enter, and then you press after that? Or is that just it?
For the guess,
Yeah.
you can just use whatever point it's at.
Okay.
As long as there's only one thing to find in between, the guess doesn't really matter. Just save yourself the hassle. You could move it close to where you think it is, but it's a waste of button pushing. How'd you guys do on the extrema? Did you get the same thing I found for your minimum?
Yeah.
That work? Okay. The last piece I'm going to need is my end behavior. I'm just going to say EB for end behavior. Is that okay with everybody? So if I look at my picture, I have two arrows. The left arrow is pointing down. The right arrow is pointing up. So left down, how do I write that again? So I do limit as x approaches, because it's left, I'm going to write negative infinity. And then my function, that guy. And then it equals, the down means negative infinity. Is everybody okay? If I look at my other arrow on the graph, the right arrow is pointing up. So I'll write the limit as x approaches, because it's right, it'll be positive infinity. And then the name of my function. And because it's pointing up, I'll write positive infinity. Is that okay with everybody? Doing all right? Not too bad?
Yeah, not too bad.
Not too bad. Okay, so this is just a little bit of vocab about, can I look at a graph of a polynomial and describe what it is that I'm seeing, find these kind of key features. If I give you the function equation, can you use your calculator to generate a graph and pull these values from the graph? We feel okay doing that? These are test questions. Same kind of thing I would ask you to do on the test. So do you have to know how to use your calculator?
Yeah.
Yes, because you cannot get these, a lot of times you will not be able to get these any other way, right? Like the techniques that you would use to actually solve these things by hand are beyond the scope of this kind of class. But the calculator can kind of bridge that gap for us and do things that we have no business knowing how to do by hand. Okay, so far so good? The rest of this chapter is going to be dedicated to solving polynomial equations. Which is equivalent to finding the zeros, or which is equivalent to finding the roots. Can kind of use all that verbiage interchangeably. That if I can do this one, I can do this one, I can do this one. Okay? So, from your Algebra 2 class, at some point you probably drew a factoring tree that looked at how to factor polynomials. I'm going to draw you the version of this that I draw. This gets quite large, so if you're at like the middle or bottom of your sheet of paper, you may want to turn to a blank page, and you may even want to write this landscape style because it kind of balloons out a little bit. So just giving you a fair warning. So the first thing you're going to look for is the greatest common factor. That's what GCF stands for. If there is a greatest common factor, you want to factor that off. If not, proceed to the next step. The next thing we want to look at is the number of terms. So if it has 2 terms, if we have 3 terms, if we have 4 terms, or if we have 5 or more terms, we're going to have a different path down our factoring tree. Now you see why I suggested landscape style, right? Because this thing gets a little bit wide. How are we doing? Do I need to pause here, or are we okay? All right. So the next thing we're going to look for is a difference of 2 squares. If there is a difference of 2 squares, we factor it. Then we have to check each factor. Down the 2-term branch. Okay, so we came down here, it says yes, we get these 2 factors. We have to check each one of those then down the 2-term branch to see if there's more that we can do. If it's no, so the next thing we check, is it a sum or difference of 2 cubes?
also check the attachment factor for 2?
2. Check the 2-term factor, because you can get a 2-term and a 3-term when you do a difference or sum of 2 cubes. This one is never factorable if you've done the order that I've suggested. The 2-term piece might be.
Just check each factor for
2 terms.
only after.
Yes, you have to cycle back through. Because you just created an A minus B and an A plus B. Each of those are 2 terms, so you have to check to see if there's more factoring you can do on those. So you have to send that back down through the 2-term branch. Check again. That's what.
Can I go to the bathroom?
Sure. Can I move? Okay. Am I good? All right. Going to the 3-term. Now, oops, just deleted something. So if you have a 3-term polynomial, the first thing you want to do is check to see if you're in the quadratic form. So if you need, like, the degree of the first x is 2 times the degree of the second x, and the third term is constant. So obviously, like, ax squared plus bx plus c is quadratic, but so is ax to the 6th plus bx to the 3rd plus c. That's also in the quadratic form, which we can still handle things that look like that. So if it is quadratic, we're going to check then to see if the leading coefficient is equal to 1. If the leading coefficient is equal to 1, then we can do our short factor and go directly to our 2-term, okay. I'll just put a question mark after it. When I say short factor, it just means, like the two things that multiply to give you C and add to give you B, and it takes you straight to your factored result, right? If it's like x squared plus 5x plus 6, the two things that multiply to give us 6 and add to give us 5 are 2 and 3. So that factors x plus 2, x plus 3. Right? You remember doing this? Yes, Adrian? Sure. If the leading coefficient is not 1, we see if we can do the long factor. Remember, for the long term, or the long factor, you have to find the two things that multiply to give you A times C and add to give you B. You use those two numbers to break up the B term into two chunks, and you have to factor by grouping. We'll review this with its specific examples, but I'm just kind of rehashing what I mean by short factor and long factor. I'm going to stall here because I still see people writing. So if it's 4 terms, again, yes? Sure. We're going to try factor by grouping. If it works, we factor it, and we have to check each of those factors down the 2-term branch. And if it's 5 or more terms, we just stop. Now, by the end of this chapter, we're going to have another procedure that we can staple on to these stops in the 3, 4, and 5 term paths, where there's still some more stuff we can try to factor them. We'll be stapling that on as we go. For right now, we're going to treat it as a stop, because right now we're just reviewing these basic factoring techniques. Pull up that, grab some specific examples. All right. Let's run through some examples. Now using this factoring tree, okay? So, it says find the zeros for this polynomial. The first step into finding zeros is going to be to factor. So if I look at my factoring tree, what's the very first step I do? Yes.
Factor out an x.
Look for a greatest common factor, which we see there is a greatest common factor of x. Everybody okay there? What do we do next? We look at the number of terms. How many terms do we have? 3. We go down the 3-term branch. We then look to see if we're in the quadratic form. Are we in quadratic form?
Yeah.
Yes, right? Okay. After that, we look to see if the leading coefficient is 1. What's the leading coefficient here? 1. Then that tells us we should do the short factoring. So we need to look for the two numbers that multiply to give us -8 and add to give us -6. Let's make that +8. I think that's just a typo. God, stop. What are those two numbers?
Or
-4 and -2. Everybody agree? So that allows me to go straight to my factored form. If I look at my factoring tree, what does it tell me to do after that? I'm supposed to check each of these factors down the 2-term branch, right? So I just kind of scroll back up and just illustrate what I'm doing. So 2 terms. X minus 2 is my first one. Is that a difference of 2 squares? Heck no, because it's just an x to the first. No. Is it a sum or difference of 2 cubes? Heck no, because it's just x to the first. Stop. Everybody's okay? And I do the same thing then for the x minus 3. I get to the same spot. I'm sorry, the x minus 4. I get to the same spot. This is factored. Everybody agree? Okay. This is step 1. Step 2. is I set this equal to 0. Step 3, I'm going to use the zero product property to solve for x. What does the zero product properties mean? If I have two things, and I'm multiplying together, and my answer is 0, that means that at least one of the two things had to be 0. So I can take, I have 3 things here multiplied together. I set each of them equal to 0. Is everybody okay? That's done, right? X equals 0, that's a solution already. Add 4 to both sides. X equals 4. That's another solution. X equals 2. That's the third solution. So my zeros then are or if I wanted to, I could write them as points. That way they kind of look more like x-intercepts. Could write it that way. Does this look familiar? I think you do the heck out of this in algebra too, right? Let's do another example. Okay. It says find the zeros and the multiplicity of the zeros for the function. We haven't defined what this is. Who remembers from Algebra 2 what multiplicity means?
Isn't that like when it like bounces or?
Okay. What if you're not looking at a graph? You're right. Multiplicity has to do with the graph. But what if we're not looking at the graph? So it's just going to be the number of times that solution occurs. So if I get the answer x equals 1 happening 3 times, that means x equals 1 has a multiplicity of 3, which would be related to how the graph crosses the x-axis. In that case, you'd have a bend as opposed to a bounce. Okay, but we're still finding zeros, right? I can't do the multiplicity until I found the zeros. So to find the zeros, my first step is to factor. When I'm factoring, what's my first step in factoring? Greatest common factor. What is the greatest common factor in this case? X. Does there have to be one? No. Okay. How many terms do I have? 3. Is it quadratic?
Yes.
No.
Yes. Is the leading coefficient 1? Yes. So I can short factor this. What are the two numbers that multiply to give us 9 and add to give us 6? 3 and 3. Can I factor x plus 3 anymore? Can I factor the other x plus 3 anymore? No, they're not differences of two squares, because it's a degree 1. They're not sum or differences of two cubes, because they're degree 1. I am finished. I then set this equal to 0. And then I apply the zero product property. And solve. Notice that I got a repeated solution here. So the 0 is used just one time. That means it has multiplicity 1. Negative 3 I got twice. That means it's multiplicity 2. Everybody feel okay there? So far, this feels pretty familiar, I hope. Again, I think that we typically take our time, and this tends to be a mastery level skill. Does that sound right? In Algebra 2, so we should have a lot of practice from this. Let's do story problem example. Actually, I'm going to make up one of my own here. All right. Let's say I want to find the zeros for x to the 6th minus 1. First thing I look for. Greatest common factor. Is there one? No. Okay. Then I look for number of terms. How many terms is this? 2. Down the 2-term branch, the first thing I check for is the difference of two squares. Is this something squared minus something squared? No. Yes. What squared is x to the 6th? X to the 3rd. Because remember, when I have an exponent of an exponent, what do? It's multiply. So if I follow my difference of two squares factoring pattern, I'd have this. Everybody okay? Now I'm going to take x cubed minus 1 and go down the 2-term branch again. Is it a difference of two squares? It can't be because the degree is odd, right? Is it a sum or difference of two cubes? Yes, right? So I can think about this as x cubed minus 1 cubed. Everybody agree? So if I look at my difference of two cubes factoring pattern, I get that. Now let's look at the x cubed plus 1. I also have to take that down the 2-term branch. Is it a difference of two cubes or two squares? No, the degree is odd, it can't be. Is it a sum or difference of two cubes? Yeah, it's a sum, right? So if I use that sum or difference of, or the difference, so sum of two cubes factoring pattern, I get this. Everybody okay? You okay with how I filled the values into the factoring patterns? You did this last year in Algebra 2, I hope. Okay. When we do the sum or difference of two cubes, we never have to check the quadratic pieces. They're never going to be factorable, assuming you go and check for a difference of two squares first. That won't happen for us. And if I check these down the two-term branch, they're linear. There's nothing I can do with those, right? So this is factored. So I'm going to set it equal to 0. I apply the zero product property. Set each term for each factor equal to 0. Two of them are very easy, right? How am I going to do the other two? Yeah. What type of function are those? Quadratic. How do I solve a quadratic function if I can't factor it?
Quadratic formula.
The quadratic formula. Who remembers the quadratic formula?
X is equal to negative. E squared minus 4ac.
That's a reasonable expectation at this stage of the game that you have memorized. I'll give it to you, but I'm going to tell you right now, for those of you that are going to college next year, that's something that your professor would expect that you have memorized. So on this guy, my A is 1, my B is 1, and my C is 1. Bye, Eddie. Oops. So silly. Everybody okay there? What do you notice about both of those solutions to the quadratic? They are imaginary. Yes. How did I know that I got those i's? What caused the I?
Negative square root.
The negative under the square root. Very good. Guess what that means? Since they're imaginary. Guess what they're not? They're not zeros. Why? Does the graph cross the x-axis? The x-axis consists of only real numbers, so my zeros are just 1 and negative 1. Is everybody okay? Now you see why I have the factoring tree layered the way I did, because sometimes you have to make several passes through before you kind of make sure everything is factored all the way. That's one where you had to do 2 passes. You could easily come up with something that required 3 or something passes through. It would not be too difficult for me to do that. Everybody okay though? I think this feels, well, I should do this story problem example. We'll do one more example problem and we'll be done. Sound good? Yes, sir. I mean, ma'am. Oh, absolutely. Here it says a company wants to create a cardboard box with an open top. The box needs to have a volume of 500 cubic inches and is to be created by cutting squares from each corner of a rectangular piece of cardboard in order to create tabs to fold up. The piece of cardboard is 26 by 20. What size squares should be cut from each corner in order to create the proper volume? So let's kind of sketch a picture of what this thing has to look like. So here's our sheet of cardboard. I've labeled the length and width of it. And then it says we're going to cut some squares out of the corners here. Since they're squares, I know that thanks.
We're turning your students.
It's a long potty break, girls.
They got stuff, I'm sorry.
Sometimes that happens to me when I'm pooping too.
Yeah.
Is everybody okay with the picture I've drawn? Now, this thing needs to be a box, right? We're folding this up to make a box. What is the volume equation for a box? Is it like geometry?
Length times height
That's
times width.
There you go. Length times width times height. Perfect. How many different variables is that for the volume? 3. How many variables do I want it to have? 1. So I'm going to need to eliminate some of these variables. So if I think about this, the length of this box is going to be like this side, right? Just that little section. The width of my box would be like those parts. Everybody agree? And then when we fold this, when we fold up these tabs, the dashed lines, those would be like the heights. So everybody can visualize what's happening here? I think the color coding is helpful, right? So I can rewrite the height as an x. That should be easy to do, right? We see that the blue is just an x. So I'm going to rewrite this volume as a function of x. So how can I rewrite this length as an expression in x? Well, how long was it from here to here? 26. And what did I remove off of that 26? An x and then another x. So this length here should be minus 2x. Everybody agree? And then how can I find the width? Well, from here to here is 20, and I've taken off, I've removed this x and this x, so similarly this will be and we're told this volume has to equal 500, right? To solve this equation, I'm going to find the zeros, but I'm not going to do this algebraically because I look at this and this looks like yuckarooski. I don't want to have to FOIL this whole thing out and do all that mumbo jumbo. You know what I am going to do? I'm just going to graph it on my calculator. I'm going to use the calculator to solve this. Ah, come on. Come on. Fine. Put it there. Just do something. Oh my God. Please. Just like work for me a little bit. Oh, heavens to Betsy. All right, fine. So into my calculator, I'm going to type my function that I'm solving. My y1 is just going to be the 26 minus 2x times 20 minus 2x times x. My y2 is going to be the 500. Everybody's okay here? Now, I'm going to have to pick a window now to find the intersection of these two things. Let's think about what are some realistic values for x. X is like the amount of distance we're going to cut out. What's the smallest possible x we could cut? How about 0, right? 0's probably, 1's fine, but like 0's realistically, that's better. What's the biggest possible x I could cut? Not 20. 10. Because what's going to happen if x is bigger than 10? That'd be negative, and we're going to have a negative volume, and we know that can't happen. Everybody feel good? Now, what y value do you know we have to get at least to? 500. So I'm just going to go on my y0 to like 600 or something. Sound good? Let's hit graph. What am I looking for? The intersections. Now, if I subtracted the 500 over so it was equal to 0, then I could look for the x-intercepts. But I'm just going to leave it the way it is and just find the intersection. It's kind of doing the same thing. Oh my God, come on. So x equals 1.2 has one answer. And then if I find the other one, oh my God, come on, get there, get there, get there. $7.02. Everybody feel okay? And then I could plug those in to get the dimensions for length, width, and height, respectively. But that's the idea. you guys at this point should be able to do 1 through 12 and then 15. I didn't do 3 and 4. Nope. So 5 to 12.
Yeah.